In my last lecture, we discussed on the wire bonding as well as the chip bonding. We have covered the solder die bonding, epoxy bonding, and eutectic chip bonding. After that, we have discussed the several wire bonding techniques like thermocompression, ball and wedge bonder, ultrasonic wire bonder, etc. Now we will discuss an different kind of bonding technique which is known as the beam lead bonding of beam lead chips, and it looks like this, the total thing, where the wires are not used, but some lead materials are used, where the total chip, all the bonding pads are fixed with the beam lead in a particular sequence. In this particular case, chips are bonded on beam lead by thermocompression bonding. This is the bonding probe which is heated, and this is the compliant material, and here is the chip beam lead integrated circuit, and this is the thin film substrate on which the chip is fixed. Now you can see one by one, this is on the substrate you put the beam lead integrated circuits, then you apply this compliant material, and using the bonding probe head, it is pressed, and you will get the chip bonded on to the substrate. This is known as bonding of beam lead chips. Heat and force to the beam leads are applied through an aluminum compliant. They are protected by thin silicon TVR rubber. Another technique is known as transfer bumping operation, and in this particular case, you see these are the bumps, the gold bumps, and these bumps are formed on the bonding pads on the chip, and then some the film carriers, some film, these are the strips of, say, either gold strips or gold along with some other material, is a adhesive material, epoxy material is used sometimes. So they are placed on the bumps, and all the films carrier and the bumps are pressed here, and then the bonding is done at one stroke, not individual bond pad is bonded with some aluminum or gold wire. The gold bumps are formed here first by preforming plating operations on a substrate. So these are put on the substrate. This is the first job. You see the bumps are put here on the substrate. These bumps are then transferred to the aligned tips of the tin plated copper foil. These are the tin plated copper foil through a bonding operation to formulate gold tin eutectic alloy, and in this way these foils, the copper coated foils, are bonded on the pads which is covered by gold bumps. So this is known as transfer bumping operation. These bumping beam lead techniques or transfer bumping operations are applicable where the pin counts are large. One of the limitation of the wire bonding technique, either it is a ultrasonic wire bonding technique or is a thermocompression ball and wedge bonding technique, there you cannot increase the pin counts high. And you know, the present VLSI area, VLSI technology, pin counts are going up day by day, so alternative wire bonding techniques are evolved, and in these wire bonding techniques normally we use this transfer bumping operation or the beam lead techniques. Now I am coming to packaging. So first job is over, that is first job is chip bonding, then comes wire bonding, second job is wire bonding, and after that packaging. So you have to protect the chip from outside environment. Now in this particular slide I am going to show you what are the purposes of the packaging of VLSI chips. So that means before packaging, what are the points we have to consider for selecting a particular package material, and at the same time what are the sequences we have to follow for packaging or assembling the wire bonded and die bonded chips. The points which have to consider for packaging are as follows. First, to provide electric connection for inside outside communication. The purpose of packaging is to provide electric connection for inside outside communication. Second objective is to provide a proper thermal path for heat dissipation. Third is to protect the circuit from outside world. For protection of the circuit from outside world means what protection? First protection is from heat and humidity, because the application areas of the chips may have lot of humid components, and you may use the chips in an environment where temperature is high. So you have to protect the circuit from that high temperature and humidity. Second protection is mechanical stress, as the mechanical stresses appear due to the pressure, vibration and shock. These are the mechanical agitations from which stress may be developed, and because of that stress there is a chances of damage inside the bonding or the interconnection area on chip. So that means you have to protect the chip by proper packaging in order that it will not affect by mechanical stresses. Third is abrasion and corrosion and dirt. Next protection, we require environmental stress, that is radiation, light irradiation, etc. Because if you want to use a chip in radiation environment, it has to be protected from the radiation, otherwise the radiation may cause a lot of damages inside the bulk of the semiconductor material, and those damages will deteriorate the performance of the chip. At the same time, light irradiation, ultraviolet or other lights irradiation on the chip may also damage, because they can induce the carrier which are thermally generated, and because of the generation of those light induced carriers, the performance of the chip may be degraded and leakage current in many cases may increase. So we have to do something while packaging so that those packages are protected, that means chip inside the package are protected from environmental effects like radiation and light irradiation. And next one is electrical effects. Electrical effects means high field. That means we may have to use the chips in a high field environment. High field means high electric field or magnetic field. So there, because of the high field, there is a chance of carrier generation, and they also damage the circuit. Also nowadays, another thing we have to consider, which is the EMI EMC protection, that is electromagnetic interference and electromagnetic compatibility. Those points has to be considered when we are choosing certain VLSI packages, and because of those considerations, selection of a proper package is not so simple. And another last one is protecting the outside wall from the circuit. That is also important. So far we discussed by ABC that how to protect the circuit from the outside environment. At the same time, we have to think also the outside environment should be protected from the circuit, because in some cases when the circuit function, VLSI circuit functions, it may emit some of the electromagnetic radiations in high power circuits, and in some cases it may generate some of the rays. The photo emissions also may take place in some of the photonic chips or photovoltaic chips. So that means in outside world has also to be protected from these hazardous rays or radiations from the chip. That means both outside environment should be protected from the chip, and chip has to be protected from the outside environment. Both should be satisfied in a proper packaging technique. Now I'll discuss on several packages. A typical hermetic package is shown in this diagram. Is a typical hermetic package. These are the metal leads, and inside here this is a chip, and chip is bonded. Chip bond pads is fixed with the metal leads using some wire. You can see these wires. So these wires are gold, aluminum or gold wire are used for bonding. You can see here, and these the metal leads are coming out external world, and there is a sealing ring, so that a hermetic seal is to be done. After putting the chip, then the wire bonding is being done, then you put the seal. And total process is like this. A silicon chip is placed in the cavity of a ceramic based package. This is a ceramic based package, and wedge bonded to make electrical connections to the terminals. These are the terminals. Metallized traces, usually tungsten, form electrical paths on the package. This metallized, these are using tungsten metal traces. So they provide electrical paths on the package. Lead sealing makes the cavity hermetic. So this is the sealing ring. On top of that you can have your upper lead, and it will seal, and it will protect outside environment. Some gas leakage or humidity environment also can be humidity protection can also be done. So this is the picture of a typical hermetic package. Now a typical plastic package is shown. Now this is a plastic package. You see, this is the spot plate, these are, and these are the lead frames, and this is the chip, and here is a chip support paddle. This is the wire which is bonded, and after the wire bonding is over, then you can use a mold, the molding compound, which usually used to for plastic molding. Okay, on the chip you will put some passivated layer which will protect the chip from the molding material. Then you can use the plastic mold. The package, the typical plastic package which shows here, is a composite structure consisting of a silicon chip, a metal lead frame, this is a metal lead frame, and a plastic molding compound. This is the plastic molding compound. The chip support paddle and inner tips of the lead frame are silver plated. The external leads are solder plated after molding. They are solder plated. Now another packaging technique is known as tape carrier package, which is known as TCP in short, is shown here. TCP is a generic term for packages in which a tape automated bonding, this is the tape automated bonding, which is known as tab technique, is used for the pad on chip interconnects. So here are the chips, these are the pads and interconnections. So now the tape is moving in this direction, and when a particular configuration of the bond pads are coming, these are basically the bonding, tape bonding pattern. When it is coming onto a chip, a die attached station is there, so they press it, automatically bonding will be done. So TCPs are usually plastic based and are used today for VLSI devices. Tape is formed, this tape which is rolling from here to here, this is formed by plating 25 micron copper layer on 75 micron polyimide based tape. So this is 75 micron polyimide based tape, onto it a copper is plated. So this is the tape is formed in this way, and the technique is known as tape automated bonding. This is basically tape carrier packaging. Next, I will discuss on bonding of chips to the tape carrier to lead frame. How it is being done? This is the diagram. Tape automated bonding uses finely patterned thin metal, usually copper foil, plated with gold or tin. In place of wires, and connects the metal tips metallurgically to corresponding bumps formed on aluminum pads on the chip. Tab has become a choice in finer pitch interconnects for high I/O ULSI devices, high input output ULSI devices. This technique is used. Tape carrier package and connection to the lead frame. This is a lead frame at a station, it is moving here. So you see the particular chip is here. If you press is a lead frame, so you press it, and here you press it, so this and this will be attached together, and you can achieve high pin counts using this technique. So that is the tape carrier to lead frame bonding. LSI package standards for chip carrier assemblies are like this. This is the flip chip technology. Using flip chip technology, you can also increase the pin counts. This is the ceramic cover. Bottom metallized pad is here, and this is a metal sealing lid. The edge conductors in grooves. The epoxy plate, okay, and flip chip technologies fabricate bumps, lead tin bumps on aluminum pads on chip and interconnect the bumps directly to the package media, which are usually ceramic or plastic based. Now, multipot transfer mold system. In this molding process, we can directly mold the package chips with the lead. Thermoset molding materials, that is epoxy compounds, are usually transfer molded in large multi-cavity molds. After it enters the pot, the molding compound is usually preheated, melts under pressure and heat, and flows to the mold cavities containing lead frame stripes. These are lead frame stripes with their attached chips. The lead frame often has long, fragile fingers, and the chip is interconnected to these leads with 25 to 30 micron diameter gold wire. To avoid damaging this fragile structure, the viscosity and velocity of the molding compound must fall within certain range. Commercially, molding compounds are designed to meet these requirements when molded at approximately 175 degrees centigrade and at a pressure of about 6 megapascal, where the upper and lower molding dies are pressed at pressure of about 18 megapascal to avoid resin flashes. Now, what are the specific features? They are plural RAM pot, runner sets, these are the runner sets, small mold compound tablets, each large enough to fill a few cavities. They are used in these arrangements. This provide better process control compared to a single pot system. It provides more stable process control than other techniques. Now, I'll show you some other IC package configurations. Here is a flat pack. This is known as a deep dual in package. This package is special packages and non-standard packages are shown. This is known as a TO5 package. The package requirements when you are selecting a particular package are as follows. It must have lead solderability and bondability. It must have higher strength to tackle high temperature and mechanical pressures. It must withstand heat for soldering the leads onto actual circuit. Electrical requirements are also to be fulfilled. So leads has to be high conducting, there should be a common ground connection, etc. Configurations are flat packs, dual inline package which is known as a deep, this is the deep structure. TO type, this is a TO5 is shown here, TO types, non-standard, these are non-standard packages. Okay, so these are few package configurations shown here. There are a lot of other configurations available in market nowadays, and those configurations are mainly in the two types. One is known as thorough hole mount, another is surface mount packages. Thorough hole mount packages may be single side or it may be dual side. Dual sides are deep, you are using both pins are coming on both the sides. There are some packages where you can have pins coming out from the four sides. Surface mount packages are SVP, there is a surface vertical mount package. Dual side there are packages known as SOP. SOP is a small outline package. TSOP, these are thin small outline package, and SOJ, these are small outline J-lead package. And another surface mount package when the leads are coming on the four sides, these are two sides coming, if it comes on the four sides of the either flat pack or deep, then they are known as quadruple side surface mount plastic package, and they are known as QFE, which is quad flat package. Another quadruple side plastic package known name is TQFE, which is a thin quad flat package, and other is QFJ, quad flat J-lead package. So these are all plastic packages. Other than plastic package, the hermetic ceramic packages are also there. They are broadly classified into two categories. One is known as thorough hole mount, another is surface mount. Thorough hole mount package, dual side and full surface is also available. Full surface is pin grade array, that means small pins are coming surrounding the chip, and another is known as SAR deep dual side. And surface mount quadruple side package name is SAR quad. So these are the variety of packages which I just now mentioned. Not all packages varieties are shown in this diagram. Some are shown and some are just I mentioned are used in many VLSI and packages. Now I will show you the inside of two typical package, which is metal can package TO5, how the inside looks like. Another is ceramic flat package, how inside it looks like. So these are the leads coming out. This is the metal can, this is a lead, this is a metal base, and these are the wares, either gold or aluminium. The leads are coming through thin glass seal. So just now, as I told you, there are three types of surface mount plastic packages. One is QFP, QFJ, and TQFP. QFP is used in logic microprocessors packaging, and they requires up to approximate 300 pins. And this nowadays microprocessor requires up to 300 pins, and this TQFP or QFP, they can provide the large number of the IO pins. So typical deep packages are shown, and their detailed dimensions, separation between two leads, etc. are also shown. Deep is basically a through-hole package which are available in hermetic, ceramic and plastic type. They provide easier placement for soldering and stronger solder joints. However, they sacrifice design flexibility and restrict mounting density. Today, over 50% of the packages use surface mount type. So now we discuss various kinds of packages. Also, we mentioned the chip bonding and wire bonding techniques. And to summarize this packaging and assembly discussion and the future trends, I would like to give you certain features as well as the future trends, namely the package pin count will continue to increase with increasing IC complexity. So aluminum ceramic packages and post transfer mold plastic packages will dominate most of the ULSI packaging technology. If chip integration keeps pace with decreasing feature size, today's interconnection technologies, especially wiring, bonding, will be challenged highly. TAB means tape automated bonding, and flip chip technologies will be the candidates to replace wire bonding in future ULSI era. Interconnections of high IO input output will have to be the choice among the technologies of wire bonding, TAB and flip chip. Interconnection IO pin numbers in future may exceed 500 per chip, then we have to go for either TAB or flip chip technology. Wire bonding cannot support that much amount of IO interconnection. System design will depend on optimization of entire interconnection scheme to achieve the potential benefits of improved silicon capability. These optimization may lead to completely new requirements for assembly and packaging, for example, multi-chip modules. With this summary and future trends, I conclude the chapter assembly and packaging. Now, with assembly and packaging, the VLSI technology course is going to be end, and now is a high time to summarize or give you a summary of the VLSI technology course, which I discussed over about 47 lecture hours. So now I am summarizing the complete VLSI technology course. In this particular course, I have taken 47 lectures, and it's spreaded over 3 phases. And in phase 1, the subject was introduced with an overview on VLSI design and technologies. I have discussed also yield and cost estimation of VLSI chips. Then comes phase 2, What I did in phase 2 is I gave you an in-depth analysis on various unit processes in VLSI technology, namely contamination and wafer cleaning, oxidation, diffusion, ion implantation, photolithography, etching, CVD, chemical vapor deposition, various CVD techniques and their principle and the physics of chemical vapor deposition, the kinetics of different deposition techniques has also been discussed, and physics of dry etching process is also discussed in depth. Then we discussed on epitaxy and finally metallization. Various metallization schemes were presented, among which some of the schemes are very new and is going to adopt in near future in VLSI technology, that is copper metallization, and the problems of copper metallization has been addressed and how to circumvent those problems that has also been mentioned. And then comes phase 3. In the phase 3 module, I discussed on process integration of VLSI and ULSI, which included isolation technology, bipolar, MOS and BiCMOS process technology. Also, I gave you some of the recent and modern VLSI processes which is being used in at present 0.18 micron technology, where the packing density is extremely high. For high speed VLSI circuits, what are the process one has to follow? What are the problems in getting high speed chips and how to remove those problems, that has also been discussed in detail during the CMOS VLSI process and advanced bipolar VLSI process, as well as in BiCMOS processes also. And I hope in the 3 phases I have been able to give you the total picture of VLSI technology, VLSI processes, and at the end I also discussed the packaging technology of VLSI chips, what are the modern packages which will be used in future, and what are the future direction of assembly and packaging that I mentioned in my last lecture. At the end, my duty is to give the references from where I have taken the documents, figures and materials for this video course, and those references have been taken from various journals and magazines and books. I acknowledge authors to the authors of those journals and books, and also the magazines from where different pictures have been taken. Suggested reference books for the video course VLSI technology are given below. You can consult these books for further upgradation, further knowledge of individual topics. Those books are namely SMZ, VLSI Technology 2nd edition by McGraw-Hill, which was published in 1998. The second reference is the C.Y. Chang and SMZ edition, that is ULSI technology, not VLSI, this will be ULSI, not VLSI. McGraw-Hill Publication Company, and 1996 it has been published. Third is S.A. Campbell, The Science and Engineering of Microelectronic Fabrication, is Oxford University Press, 1996 publication. And the fourth is S.K. Gandhi, VLSI Fabrication Principles, Silicon, Gallium Arsenide, is a Wiley publication in 1983. These are the 3 textbooks which have been used in preparing these lecture materials, and I will advise the students to follow these books in future. If you have some problem while going through these video lectures, you can consult those books and you can have detailed information on a particular topic. With this, I conclude the video lecture on VLSI technology. I hope you enjoy the lectures. Thank you. you.